Okay, continuing on with our logarithmic functions. Let's look at our next set of examples here. We want to know which one is larger, the log of 10 base 3 or the log of 40 base 7. Now recall, logs are just ways of expressing the exponent. So the log of 10 base 3 is just asking us if we take 3, get my pen working here, what exponent do we have to raise it to approximately get 10? Well, we know that 3 squared would give us 9. So that means that our exponent would have to be a little bit bigger than 2, because 3 cubed would be 27, and that's pretty far away. So just a little bit bigger than 2, where the log of 40 base 7 is asking us, if you take 7, a base of 7, what exponent do you have to raise it to get 40? Well, here we know 7 squared would give us 49, and that's too big, so here we know that our exponent would have to be smaller than 2. So which one is larger? Well, the exponent bigger than 2, so the log of 10 base 3 would be the larger number. Okay. On example 2 and example 3, we are given logarithmic functions and we want to find the domain. Well, recall with your log functions, your log graphs, okay, that was these graphs, our domain always had to be something that was greater than 0 because we had the vertical asymptote at x equal to 0 with our basic log graphs. So anytime you are looking at log functions, you are going to have restrictions on your domain. So prior, we would have restrictions if we were working with even roots or if we were working with rational functions where we had variables in the denominator. Now you can add to that list. Anytime you are working with logarithmic functions, you're going to have restrictions on your domain. You're going to need to check your domain. One, number 2, if we are taking the natural log, our function is the natural log of x plus 5, we want to find the domain. Well, anything you take the log of, in this case, we are taking the log of x plus 5, the natural log of x plus 5, we need that quantity to be greater than 0, because our domain with our basic logs is always something that is larger than 0. So if x plus 5 needs to be greater than 0, that means that x needs to be greater than a negative 5. So our domain on number 2 is a negative 5 to infinity, not including the negative 5, because we cannot take logs of 0. Remember, we will not hit the x-axis with our basic log graph. On number 3, we're taking f of x is equal to the log of 12 minus 4x base 2. We want to, that should be a D, find the domain. Well, your logs can only take logs of quantities greater than 0. So the expression that you are taking the log of, 12 minus 4x, needs to be greater than 0. Or in this case, 12 has to be greater than 4x, or x has to be less than 3. So our domain is going to be from a negative infinity up to 3, not including our 3. So the base, whether it was base e on number 2, base 2 on number 3, is not going to impact the equation or the inequality that you need to write when you are solving for domain, because it is the quantity that you are taking that you need to figure out is greater than 0 for your domain quantity. On number 4, looking at our graphs, going back to our idea of reflections, translations, all of that is going to come in play as it did with our exponentials, same thing with our logs. So our basic graph of log of x base 3 is this function that is increasing from quadrant 4 up into quadrant 1, where we know it's going to go through at 1, 0, and we have this vertical asymptote at x equal to 0. Our domain, we know, has to be something greater than 0. Our range is going to be everything. We've got that x-intercept that we put down at 1, 0, y-intercept that is not going to exist, and that vertical asymptote that we just put at x equal to 0. Now the base 3, whether it was base 3, base 4, base 10, just the same idea with our exponentials. The larger the base, the steeper the graph. Well, the same idea is with our logarithmic graph. So the larger the base, the closer to the x-axis our graph is going to become. Just like with our exponentials, the larger the base, the closer to the y-axis our graph would become. But the general idea, the general form is it's increasing from quadrant 4 into quadrant 1, and that's what we're focusing on right now. So minus the log of x base 3, well, we know that if we have a negative that is out in front of the function, where we are negating that function, we're negating the y values. Anytime we negate the y values, that means we're reflecting over the x-axis. So if we take what was our graph here, and we just flip that over the x-axis, and our graph is doing something along those lines. We're still at that point 1, 0. Okay, we've just reflected over the x-axis. Versus down over here, if the negative is attached to the input, to the x, we know that tells us to flip over the y-axis. So if we take our original graph, which was up here, and we reflect it now over the y-axis, now our graph should be looking something along those lines. Where now this is at a negative 1, 0. If I'll let you now do this one afterwards, where you're needing to reflect over the x-axis and y-axis and see what your graph that you get there. On the next one, the natural log of x plus e plus 2.7. Remember, if we are adding to the input, adding to the x, that is actually telling us to go left, and in this case we're going left e units, left 2.7. Our basic graph was right here. That was our basic natural log of x, where we were here at 1.0, and if we shift everything left 2.7 units, that means also our vertical asymptote is going to shift 2.7 or e units to the left. So now we're going to have a new vertical asymptote over here at x equal to a negative e. We were at x equal to 0. Now we're going to the left e units. We were at the point 1, 0. And if we subtract 2.7, now we're going to be over here at a negative 1.7, or e minus 1, a negative e plus 1. So what, negative 1.7? I can write that in there. And our graph is something along those lines. But every single point would shift over a negative 2.7 units. And if we are looking at the next one, natural log of 3 minus x, or if you prefer, the natural log of a negative x plus 3, we know that the negative is telling us to flip over the y, and the plus 3 is telling us to go left. And we know that we want to translate first before we flip over the y. So if we start with our original basic graph, and our basic graph was our natural log of x, where this was at 1, and our vertical was at x equal to 0. If we go left 3 units, let me switch colors here. If we go left 3 units, that means our vertical initially would shift over 3 units. So initially our vertical would be over here, and our graph would shift over 3. And then we are flipping over the y-axis, which means we are negating our x values. So this was at x equal to a negative 3. But if we're now flipping over the y-axis or negating our x values, x equal to a negative 3 now is going to shift over here to x equals a positive 3 for our new vertical. And if we flip our graph over, so now our graph is going to be doing something along those lines. Okay, where we would have a new x-intercept over here. Okay, let's actually try and see if we can solve for some information about that graph. So I'm going to come over here on the side. Our domain for that graph, well, we know whatever we take the log of has got to be greater than or equal to 0. So in this case, our 3 minus x needs to be greater than 0, or x has to be less than 3, and that's what we're seeing in our graph, right? Our graph is going off to the left towards quadrant 2. So our domain is that negative infinity up to the 3. Our range is going to be everything, negative infinity to infinity. Our x-intercept, well, our x-intercept, we know we always set y equal to 0. So if we set our equation, come over here to the side, the natural log of 3 minus x equal to 0, this is asking us, there's a base e implied, that if you take that base e and you raise it to the exponent of 0, because remember, logs equal the exponents. So if we take base e and we raise it to the exponent of 0, it needs to equal this 3 minus x. Well, e to the 0 is just 1. And we know then that x is equal to 2. So our x-intercept over here is at 2, 0, which if we had just kind of played around with our numbers and gone from 1, shifted over left 3, and then flipped, we also would have seen that it was at 2, but we could definitely solve for that algebraically. So our x-intercept was 2, 0. Our y-intercept, we always set x equal to 0. So if we set x equal to 0, then we have the natural log of 3 minus 0, or we get the natural log of 3. And logs are just numbers. That is just representing a number. So our y-intercept is just 0, natural log of 3. And our logs have vertical asymptotes. And in this case, our vertical asymptote we saw was x equal to 3, that vertical line of x equal to 3. Okay. The earthquakes here, we'll discuss that when we meet in class. We have 2 more domain questions, 5 and 6, with domain. Let's look at, leave 5 for you. We can look at 6 real quick. But recall in both 5 and 6, when you are finding domain of your log functions, whatever you are taking the log of, that quantity always has to be greater than 0. So on 5, you need to solve for when 4x minus 3 over x plus 2 is greater than 0. And on 6, we need to solve when x squared minus 7x plus 10 is greater than 0. And if you think back to our earlier sections, Anytime you had a rational with an inequality or a second degree or higher with an inequality, you want to be thinking of your plus minus charts. So on 5, you want to be thinking of a plus minus chart. On 6, we will quickly go through and do our plus minus chart. We have our x minus 5, x minus 2. So our two key numbers, or we can actually even just do a quick graph here. We have an x-intercept at a positive 2 and an x-intercept at 5. We know our graph is opening up because our a term is positive, so our graph is looking something along those lines. So when does our graph here go above the x-axis? Well, we know it goes above to the left of 2, and it also goes above to the right of 5. So our domain is that negative infinity to 2 or from 5 to infinity. Both of those intervals would allow that quantity to be greater than 0. So a couple common errors to keep in mind. These log expressions that we are evaluating are representing numbers. So this, just like when you were working with sines, cosines, and tangents in geometry, the sine of 23, that entire quantity stays together. You cannot separate the sine or the number, the 23. So likewise, the log of 8 base 2, that entire expression represents a number. You cannot just take away the word log or take away the number 8, okay, or take away the 2's. Okay, they have to stay together. Okay. Likewise, on the log of 16 base 2, you cannot just cross out the 16s. This whole quantity is a number and it has to stay together. So just be careful when you are trying to or looking or considering crossing out quantities. Okay. Last two examples. On number 7, we want to solve for x, so we will be solving some equations. We have 10 raised to the exponent of x over 2 equal to 16. Now keep in mind before, anytime we were solving for the exponent, we were trying to get like bases. And unfortunately, we will not always be able to get like bases. If we can, it definitely makes it easier in order to solve, and I strongly encourage you to do so if you can. But if you can't, that's okay, because we can still solve. So anytime you cannot get your bases to be the same, you can take what is written in an exponential form and we can switch it to a logarithmic form. Now recall that logs are ways of expressing exponents. So for 10 raised to the x over 2 equal to 16, the exponent is x over 2. And if logs are equal to exponents, our exponent was the x over 2. So the log, our base here was 10, so the log base 10 of 16 equals that exponent of x over 2, because logs equal the exponents. Now I did not have to write base 10. Base 10 is always going to be implied if we do not write a base. So we could have just said log of 16, where base 10 is implied. Either one is fine. And we're trying to solve for x, so all we need to do now is just multiply and get rid of the 2 and isolate the x, isolate the variable by itself. So our final answer is just 2 times the log of 16 is equal to x. We can just leave our answer like that, since log of 16, base 10 implied, is not a perfect, nice number. Okay. On number 8, we want to solve for, actually this should be t. Solving for t, we have e to the 2t minus 5 equal to 5,000. Our unknown is in the exponent position. base E is on the left, 5,000 is on the right. We cannot rewrite 5,000 with a base of E, but that's okay. We can switch it to log form. We're looking at an exponential form. And recall that logs are equal to exponents, and our exponent is the 2t minus 5. So we know that that 2t minus 5, that exponent, is equal to, well, since it's base E, instead of writing log, I'm going to write ln, where base E is implied. I do not have to write the E. I'm just writing it right now to overemphasize. So the natural log of the 5,000, that base E, would equal to that exponent of a 2t minus 5. So our natural log of 5,000 equal to 2t minus 5. We just want to isolate our t, so I'm going to add 5 to the left and then divide out our 2. So the natural log of 5,000 plus 5 divided by 2 is equal to our t. Now keep in mind, this whole thing represents a number. You cannot divide the 2 into the 5,000. Okay? It is all connected. It is representing a number. Okay? So our final answer is just this whole expression of the natural log of 5,000 plus 5 divided by 2. And that is our answer for t. Okay? And we